Everyone talks about CPUs. We obsess over Kubernetes, the latest GPUs, and the endless, massive possibilities of AI. We spend our days optimizing compute power and shiny new frameworks. But almost nobody talks about the invisible system connecting all of it. Welcome to this explainer, where we're going to completely expose the hidden world of cloud networking.
See, that invisible system, the network, is exactly where cloud architecture becomes incredibly unforgiving. While we're all busy scaling up our application servers, the network is quietly dictating your true performance, your latency, your reliability, and definitely your bottom line. You can literally have the most elegant, highly optimized codebase in the world running on the absolute most expensive hardware available. But if the packets can't flow cleanly, none of it matters. By the end of this explainer, you are never going to look at cloud architecture the exact same way again.
So to really understand why, we need to uncover the invisible cloud backbone, investigate DNS and routing, expose the hidden latency trap, dissect the multi-region mirage, break down the costs nobody notices, and finally, learn how to design like an elite architect. Let's dive right in. Section 1. The invisible cloud backbone. Let's talk about why networking hides so well. So, why do perfectly healthy applications just inexplicably fail? Well, developers naturally fixate on compute. Imagine you get a pager alert at 3 a.m. You groggily log in, check the dashboard, and CPU utilization is totally fine, memory is perfectly stable, the Kubernetes pods are running exactly as expected, yet the app is completely failing and users are seeing timeouts across the board. Why? Because networking quietly orchestrates everything else. Every single API call, database query, and object storage request depends entirely on that underlying network fabric. When the network stutters, drops packets, or experiences microbursting, your perfectly optimized code simply hits a brick wall. And the compute layer? It assumes everything is totally fine, completely oblivious to the chaos happening in the wires below. Section 2. DNS and cloud routing. The internet's traffic cops.
Okay, it all starts with DNS. But in the cloud, we aren't just pointing a domain name to a web server. We're talking about highly complex internal service discovery, split horizon DNS, and massive private zones mapped across multiple virtual private clouds. Managed DNS within your VPC is the absolute lifeline of your microservices. Think about it. A single misconfiguration, or even just a stale cache in core DNS during a rapid scale-up event, can take down an otherwise perfectly healthy cluster in seconds. If Service A cannot resolve the internal IP address for Service B, your system is completely dead in the water. Compute means absolutely nothing without direction.
So once DNS actually finds the target, how does the packet survive the journey? Let's trace it. A packet leaves your instance, hitting the subnet, and immediately evaluating the route table, which is essentially the directional signpost of your entire environment. If it's a private workload reaching out to a public API, it hits the NAT gateway next. Finally, it flows out through the internet gateway. Every single hop is a deliberate, highly constrained step in transit networking. It's an intricate dance of permissions and paths. Misconfigure a single route or exhaust the ephemeral ports on your NAT gateway under heavy load, and your packet silently vanishes into the digital void. And guess what? There are no crash logs when a packet simply disappears. Section 3. The hidden latency trap. This is what happens when slow apps have low CPU.
Now, consider one of the absolute most frustrating paradoxes in cloud computing. You look at your metrics, and your compute resources are barely breaking a sweat. Low CPU usage across the board. Yet your users are submitting urgent support tickets because the application is agonizingly slow. How is this even possible? Simple, because you cannot outcompute the speed of light. Physical distance and the sheer volume of network hops create massive invisible delays. You can provision 1,000 extra cores, but if your data has to physically travel through fiber optic cables across a continent and navigate a labyrinth of firewalls and gateways, the application is going to drag. The bottleneck isn't processing power, it's physics.
We generally see 3 main culprits here. First, physical distance. If your master database is in Virginia and your application server is in London, every single query is essentially fighting an ocean. Second, TLS handshakes. Look, security is non-negotiable, but establishing a secure connection requires multiple round trips before a single byte of actual application data is transmitted. And third, the absolute worst offender in modern environments, API chaining. If a user request forces Service A to call Service B, which calls Service C, which then queries a distributed database, you've just compounded your network latency 4 times over.
This intensely chatty microservice architecture will throttle your system and leave your users waiting no matter how many GPUs you throw at the problem.
Moving on to Section 4, the multi-region mirage. Let's unpack cross-region complexity. The industry loves to hype up active-active deployments and multi-region resilience. And yeah, having your data replicated across geographic regions for true disaster recovery sounds fantastic on paper, right? It's the ultimate insurance policy. But the reality is often just unnecessary complexity and severe cross-region latency. This brings us right to the realities of the CAP theorem. If your architecture requires synchronous data replication across the country to maintain strict consistency, your application literally has to wait for data to be safely written hundreds of miles away before returning a success message to the user. Every transaction is bogged down by the transit time between those regions. Sometimes, multiple regions save your business from a massive outage. Other times, they just inject painful, system-dragging delays into every single request.
Section 5. The cost nobody notices. The massive network bill that hits right after compute.
Networking frequently becomes the absolute largest cloud expense directly following your server instances. There is this hidden matrix of costs, silently draining IT budgets month after month, often completely shocking leadership when the invoice arrives. You've got standard data transfer out to the internet, which is heavily metered. You have NAT gateways, which bill you not just for the hourly uptime, but per gigabyte of data processed through them. You have cross-AZ traffic, where you are literally paying to move your own data between data centers in the same geographic zone. And of course, the ever-ticking meter of load balancer charges based on connection time and bandwidth.
Egress costs are for sure the silent killers of enterprise cloud budgets. Now, internet egress gets all the attention, but internal traffic is what truly catches architects off guard. Cross-region traffic and cross-availability zone data transfer feel like they should be free, right? Because they happen internally within your cloud provider's network. I mean, to a developer, writing the code calling another microservice feels entirely free. It's just an API request. But at enterprise scale, moving terabytes of data between availability zones in the exact same city is heavily metered. It is absolutely not free. A poorly optimized data pipeline copying logs across regions can easily generate a 5-figure networking bill before anyone even realizes the pipeline was turned on.
Finally, Section 6, designing like an architect. What needs to happen before the workloads ever deploy? Highly experienced architects know that you absolutely must design the network flow long before you ever spin up a single container or provision a database. They ruthlessly focus on 5 core priorities. Simplicity, because complex networks break in brilliantly complex ways that are nearly impossible to debug under pressure. Least latency, which means strategically placing workloads exactly where they need to be to minimize hops and physical distance. Security, enforcing strict zero-trust network boundaries right at the subnet level. Fault isolation, designing cellular architectures so a failure in one network segment never cascades to another. And cost optimization, meticulously routing data flows to avoid those massive egress traps we just talked about. This is the foundational mindset required to survive and thrive in the cloud.
I want to leave you with this thought. Cloud networking is invisible when everything works. It is unforgettable when it doesn't. The best cloud architects don't just deploy infrastructure, they design how every single packet moves. Because when you master the network, you master the cloud.
And that brings us to the end of our explainer. If this changed the way you look at your cloud environments, make sure to like, subscribe, and share this with your team. We've got plenty more deep dives into cloud architecture, infrastructure design, and platform engineering coming your way. Keep learning, design smart, and we'll see you in the next one.